Today, we unravel the fascinating evolution of computer networking, starting from the 1950s. Dr. Smith, could you shed light on the initial stages of network development during that era?
Certainly, the 1950s marked the inception of computer networking with the rudimentary point-to-point connections. These early networks facilitated basic data sharing, reminiscent of telephone communication but for data packets. An interesting instance was the SAGE system in North America, which was an early warning defense system using this technology.
Intriguing. However, given the limited technology of that time, were these networks truly efficient and scalable?
That's a valid concern. They were indeed limited, primarily focusing on specific tasks like military communication. Reliance on physical cabling made them inflexible. However, what was fascinating is how these networks laid foundational principles that influenced later innovations in connectivity.
As we progress to the 1960s, ARPANET emerged. What notable advancements did this network bring, and how did it challenge earlier limitations?
ARPANET revolutionized communication by introducing packet switching, a precursor to modern Internet protocols. Unlike its predecessors, it allowed multiple data paths, reducing congestion and failure risk. This development was akin to moving from single-lane roads to highways, drastically improving data flow capacity.
Moving into the 1970s, the advent of TCP/IP set the stage for a networking overhaul. Dr. Smith, can you elaborate on how these protocols transformed communications?
Absolutely. TCP/IP became the universal language of computing devices, allowing disparate networks to interconnect seamlessly. This transformational leap was not unlike creating a universal railway gauge, enabling trains to run smoothly across different regions.
That sounds revolutionary. However, wasn't there a significant challenge regarding the adoption across the myriad of network architectures worldwide?
Indeed, the initial reluctance and compatibility issues posed significant hurdles. For example, AT&T hesitated to adopt TCP/IP, favoring their existing designs due to integration complexity. But eventually, the global utility and efficiency convinced many, driving widespread acceptance by the late 1980s.
So, what future implications did this foundational shift have on networking as we approached the 1990s?
TCP/IP paved the way for the World Wide Web, becoming the backbone of the burgeoning Internet. We're observing similar transformations today with IoT, where seamless connectivity is reshaping device interaction on a global scale.
Let's delve into the 1990s, the era where the World Wide Web emerged. Describe its impact on existing computer networks and user interaction, Dr. Smith.
The 1990s revolutionized computing by making the Internet accessible to the public, shifting from academic and military use to personal homes. A major catalyst was Tim Berners-Lee's invention, bundling HTTP and HTML to create browsers which made Internet navigation user-friendly, like moving from early telegraphs to personal telecommunication gadgets.
Despite its value, skeptics argued that the web was initially chaotic and unregulated. How did these concerns affect its evolution?
Indeed, early critics compared the nascent web to a lawless frontier, pointing to issues like unreliable connections and insufficient bandwidth. However, these criticisms sparked dialogues on net neutrality and infrastructure investments, whose long-term solutions have cemented the web's stability today.
In hindsight, the foresight to address these challenges reshaped society. How do you see the principles from this era influencing web experience in the future?
The last decade has seen a push towards more decentralized architectures. Blockchain technology shows promise in providing secure, transparent web experiences, echoing the transformative spirit of the 1990s revolution.
In contemporary context, the 2000s introduced transformative technologies such as Wi-Fi, cloud computing, and IoT. Could you share how these have redefined network capabilities?
Certainly, Wi-Fi liberated networks from physical constraints, akin to cutting the cord on telephones, expanding connectivity limits, while cloud computing offered scalable storage as easily as renting space in a vast city, providing ubiquitous data access without on-site infrastructure.
Interesting. Yet, with the convenience come concerns, notably data security and privacy. How are these being balanced in the current landscape?
The debate is ongoing, with IoT raising significant questions. Weak security can compromise whole networks. Agencies are crafting stringent protocols and guidelines to mitigate risks. For example, endpoint encryption and multi-factor authentication are becoming standard.
As networks continue to evolve, what emerging technologies should we anticipate, and how might they redefine connectivity?
Looking forward, quantum networking could redefine limits, offering unprecedented speed and security. While still in infancy, it mirrors the potential once seen in early TCP/IP work, with the promise to upend current computing capabilities and secure communication as we've never seen before.